Okay. Today the topic is classical optimization technique for unconstrained several variable optimization. In the last I talked about the unconstrained optimization with a single variable. Today I will talk on the necessary and sufficient condition for tackling unconstrained multivariable optimization problem. This is the model for the unconstrained general nonlinear programming problem, where the objective function is f x and the function involves n number of decision variables, and we want to minimize the function f of x. Similarly, we can maximize the function as well. Now, this is the general form of unconstrained optimization problem. Now, our aim is to find out the values for x 1, x 2, x n which satisfy the restrictions, means here only the range of the decision variables are given to us, there is no other constraint as such, and we want to minimize the function f here. Now, this is the simple example for two variables optimization problem, where we need to find out the maximum or minimum points of the function x 1 to the power 3, x 2 to the plus x 2 to the power 3 plus 2 x 1 square plus 4 x 2 square plus 6. If we see here that this function involves two variables and there is no other constraints given to us. That is why the variables are range is given, there is no restrictions on the range even. Now, we want to find out the necessary and sufficient condition for getting the minimum or maximum of this unconstrained function of several variables. Now, we will just consider a general decision optimization problem, where the problem involves n number of decision variables. That is why the necessary condition tells us that if f of x has an extreme point at the point x equal to x star, and the first order partial derivatives exist for f, then first order partial derivatives of f with respect to n number of decision variables or will be 0 at the extreme point. This is the necessary condition for us. If you remember, for the necessary condition involving function of single variable, we had the same condition. Instead of the partial derivative, there we had the first order derivative of the function. Since here the function is the function of several variables, that is why we need to consider the first order partial derivatives of f with respect to x 1, with respect to x 2, similarly for all other up to n variables, x n variable, and we will equate to 0 at the point, then we will get the extreme point x equal to x star. We need to prove it, we need to prove the necessary condition. That is why we need to prove that if x star is the optimum point, let us consider this is the point, that is the relative minimum for us, then the first order partial derivatives at x star would be del f x star by del x 1, del f x star by del x 2, like that del f x star by del x n, and we need to prove that all are 0 individually. Now, let us assume we will prove this one with the help of the Taylor's theorem. Not only that, we will prove the theorem by the contradiction process. As we know, for the Taylor series, if I just want to expand the function in Taylor series, this is the form given to this is the form, and we have considered in the after the second term, because we need to consider that the function is twice differentiable, and this is the remainder Taylor's remainder form with us. This is the number of n variables. For explaining this thing, let me explain the Taylor series in general for function of two variables. Where function is variable, there are two variables. If I want to consider, then f x 1 plus h, f x 2 plus h, in Taylor's form this would be is equal to f x 1 x 2 plus h 1 and h 2. Let me consider two increments, h 1 del x 1 plus h 2 del x 2 of f of x 1 x 2, and the third term would be 1 by 2 factorial h 1 del x 1 plus h 2 del x 2 square and f of this one. And if I just consider up to n number of terms, then it would be minus n minus 1 factorial and h1 del x plus del x1 plus h2 del x2 whole to the power n minus 1 f of x1 x2, and the nth term would be 1 by n factorial h1 del x1 plus h2 del x2 to the power n, but in the remainder term there will be the involvement of theta will be there, where theta will lie between 0 to 1. This is a very small value, and that is why this is the expression for us. If this is so, then we can generalize it for n number of variables, and if we consider that up to the second order term, then with n number of variables, the second order term, then considering number of variables, again k number of variables, here we are considering n is equal to 2 only up to the second term, not only that, k number of variables. Then we will have the remainder term only. Let me just write down the remainder term only. This term would be n factorial h1 del x1 plus h2 del x2. Since there are k number of variables, that is why it would be hk del xk to the power 2, and f of x1 theta h1 plus x2 theta h2. If I expand it further, it would be 2 factorial rather, because n is equal to 2 here. If I expand it further, it would be is equal to 1 by 2 factorial h1 square del 2 by del x1 square h1 h2 del 2 by del x1 del x2. Like that, it will just go further and further, and the last term would be h a square del 2 by del xk square, and this would be x1 plus theta h1 x2 plus theta h2. The same thing has been written here as well. Here we have considered f x star plus h at the point extreme point. We have expanded we have done the same thing, and here we are having this one where d2f is equal to summation I is equal to 1 to n, j summation j is equal to 1 to n h I h j, and del 2f x star plus theta h by a del xi del xj. The way we have written here, the same thing, this we have considered, we can consider here as 2 factorial I is equal to 1 to k, j is equal to 1 to k h I h j del 2 by del xi del xj, and f of x1 plus theta h, x2 plus theta h2, and there are k number of variables, certainly there will be k number of variables will be there, theta hk. Similarly, here as well it will just go up to xk plus theta hk. Now, this is the way we have just the same thing we have written with the Taylor series like this, and this is the expansion we need to prove. This is the necessary condition we are proving now. We want to prove that these terms are all individually equal to 0. Now, we will prove the theorem by contradiction process. We will consider all of the first order partial derivatives are not equal to 0. Let us assume that kth order first order partial derivative does not vanish. That means that del f x star by del xk is not equal to 0, and all other 0. And we will see let us see what is happening then. Again we are writing the same expression here. Here it is equal to f x star plus h minus f x star would be is equal to this term plus this one. This is this thing. Now, we are assuming here that the kth first order partial derivative does not vanish. That is why if I just write down once again the same expression, we will see that this will vanish, this equal to 0, the next one again equal to 0, up to this k minus 1th partial derivative 0, k plus 1th partial derivative 0, and the nth partial derivative is again 0, plus the kth partial derivative is not equal to 0. That is why what is happening then, if this is so, then we are getting, and again this is tending to 0 because hi and hj, these are small increments of over the decision variables. Once this is tending to 0, this is of order, this expression is of order h square. That is why this will vanish again. The whole expression then only depend on, the left hand side is only depending on the right hand side value. This is the expression for us, we are getting it. Now here if we assume, we have assumed that del f x star by del x k is not equal to 0. First let us assume that this is greater than 0. If this is greater than 0, that is del f x star by del x k is greater than 0, then what is happening? For hk greater than 0, the left hand side expression is greater than 0. For hk less than 0, the left hand side expression is less than 0, because this we have assumed as greater than 0. If this is so, then what will happen? Ultimately we are proving that x star cannot be the optimum point, but this is not acceptable to us. That is why we will conclude that whatever we have assumed that kth first order partial derivative is not equal to 0, that is not acceptable. Now the same condition we can prove similarly if we consider del f x star by del x k is lesser than 0. Only the condition here, the condition will just reverse. For h k less than 0, it will be greater. For h k greater than 0, it will be lesser than 0. That is why for the both the cases we are reaching to the conclusion that x star cannot be the optimal point, because ultimately this change of the functional value is not going to equal to 0. That is not acceptable. That is why whatever assumption we made, that is the kth partial derivative, kth order partial derivative, first order partial derivative is not equal to 0, that is not acceptable. That is why we are concluding that all the first order partial derivatives as well as the first order partial derivative with respect to kth decision variables is also equal to 0. That completes the necessary proof of the necessary condition. Now let us come to the next, that is the sufficient condition proving. In the sufficient condition, the first condition tells us that at the extreme point, if the matrix of the second order partial derivatives, that is the Hessian matrix, is positive definite, then it is relative minimum. At the extreme point, if we see the matrix of the second order partial derivatives, that is the Hessian matrix, is negative definite, then the corresponding extreme point is the relative maximum. And if we see at the extreme point the Hessian matrix neither positive nor negative definite, then we are concluding that this is the saddle point. We need to know few things to prove the sufficient condition. First of all, we need to know what is Hessian matrix, then we need to know what is the meaning of the positive definiteness, negative definiteness of the matrix in general. That is why we are now starting the proof of the sufficient condition. Again I am coming back to the expression as I have explained, that is the Taylor series expansion with after the second order, after the second term we have taken the Lagrange form of remainder. And if we just look at this expression, what this expression tells us that, as we know from the necessary condition, at the extreme point, if we consider x star is our extreme point, then certainly the first order partial derivatives all will vanish together. That is why only the left hand side expression, that is f x star plus h minus f x star, is only depending on the term, that is 1 by 2 factorial, summation, double summation over I and j, both are running from 1 to n, h I h j del 2 f x star theta h by del x I del x j. If just I have showed it to you that this expression is nothing but an expression that is second order, which involves second order partial derivatives. I will talk more on this. The only thing just I want to mention here, that the sign of the change of the functional variable is fully dependent on the sign of this expression. Let us analyze further what this expression means. As we see, this expression is in the form is a quadratic form. and this is quadratic form. What is the meaning of the quadratic form we need to know? Not only that, we will show you that this quadratic form will have the form with the Hessian matrix in this fashion: H t capital H small h at point x equal to x star. And one thing just I want to mention, that if you remember, the last order term was involving the theta, that is the remainder term for us. Since x star is the extreme value for us, extreme point for us, in the neighborhood of x star, this del 2 f x star by del x I del x j will have the same sign with del 2 f x star plus theta h by del x I del x j. That is why we can say that the sign of f x star plus h minus f x star is fully dependent on the sign of this expression, and this expression is in the form of in the quadratic form. That is, this quadratic form is very much related to our matrix notation, and this quadratic form, there are three terms within this. One is h t, h is the vector we have considered, h is h1 to hn vector, capital A is the Hessian matrix for us, and small h is the same vector. The first one was in transpose fashion, and this is in the normal, and this vector at the point x equal to x star. That is why we are concluding here that the sign of the function is fully dependent on the quadratic form, and this is the Hessian matrix for us. If I just write down in detail, then we can write down the expression, this one. Just see this expression, we were having h I was running from 1 to n, j was running from 1 to n, h I, h j, del to f, del x I, del x j. This thing can be written as h 1, h 2, h n, that is a transpose of the column vector, and in between we are having the Hessian matrix. How Hessian matrix looks like? Just I will just write down in the next, and this is the column vector for us, h n. That is why this is taking the form h t, h, h, as I showed you, and this h is in the form of del 2 f by del x 1 square, del 2 f by del x 1 del x 2 dot dot del 2 f by del x 1 del x n. Similarly, the next row would be del 2 f by del x 2 del x 1, del 2 f by del x 2 square, del 2 f by del x 2 del x n, and similarly we will get the last row as well. That is why I can say this is the Hessian matrix for us. That is the Hessian matrix, as I showed you. This is the Hessian matrix for us, and this Hessian matrix is being written with this term. This is the notation we are using for the Hessian matrix. That is why we are saying that the sufficient condition is fully dependent on the quadratic form, and the sign and the rather this is fully dependent on the property of the Hessian matrix. And if we see here, f x star plus h minus f x star is greater than 0 if q greater than 0, and f x star plus h minus f x star is lesser than 0 if q lesser than 0. That is why we can conclude that at the extreme point x equal to x star, if q greater than 0, then the Hessian matrix must be positive definite, and if q less than 0, then the Hessian matrix must be negative definite. How the quadratic form is related with the positive definiteness of the Hessian matrix, that I will just tell you in the next. But one thing it is clear that at the extreme point, whether the extreme point is minimum or maximum, that fully dependent on the sign of the quadratic form. That is why we can conclude that if the sign of the quadratic form is positive, then certainly the function is having the minimum value, relative minimum value. That is why we can say at the extreme point, at the relative minimum point, matrix of the second order partial derivative, that is the Hessian matrix, is positive definite, rather the corresponding quadratic form is greater than 0. Similarly, we can say that at the relative maximum point, the Hessian matrix is negative definite, rather the quadratic form is lesser than 0. But if we see at the extreme point where the Hessian matrix is neither positive definite or negative definite, that means we cannot conclude whether the quadratic form is positive or negative, then we will say the corresponding point is the saddle point for us. That is why before going to the detail of any example on the unconstrained optimization problem involving n number of variables, let us just go through the properties of the quadratic form first. If I see that if there are n number of variables, this is a polynomial of degree 2. How the polynomial look like? This is a quadratic homogeneous polynomial. There are terms are there, the terms can be written summation aij xi xj. Here q is equal to a11 x1 square plus a12 x1 x2, like that a1 and x1 xn, like that we will get all the terms from this summation notation. This is the quadratic polynomial for us. This quadratic polynomial is very much related to our sufficient condition for unconstrained several variable optimization, because as we see that whether the extreme point is minimum or maximum, that fully dependent on the sign of the quadratic form. If the sign of the quadratic form is positive, then we can see that the corresponding the extreme point gives us the relative minimum value. That is why the sign of quadratic form is very important for us. That is why I am just going through that part of matrix algebra which we need further. Now, this can be written in the form of, just see, this expression can be written as in the matrix notation xt ax. Now, one thing it is here, instead of taking a11, a12 etc., if I just change the term in this way, I want to change the matrix A to a symmetric matrix. That is my target. That is why what we will do, we will just change all the coefficients with this form. Cij is equal to aij plus aji divided by 2. Then the corresponding quadratic form will be a quadratic form which involve the symmetric matrix. Symmetric matrix means if A is a symmetric matrix, then A must be is equal to A transpose. That is why we will just see how the symmetric form we are getting in the next. That is why we can say that this is the symmetric matrix. This should be xtcx, and where C is a symmetric matrix. Let us see with an example here. If I look at this example, what we see here, this is the quadratic form given to us. Q of x1 x2 is equal to 10 x1 square. This is a homogeneous quadratic polynomial x2 square plus 2 x1 x2. If I want to write in the form of this way, just xt ax, then I have to write this one as x1 x2 10 4 2 0 and here x1 x2. Now, here you will see that this matrix is not a symmetric matrix. If I want to make this matrix as a symmetric matrix, we will just use that equation as I have told you. We will just take aij plus aji. That is why this matrix will become 10 1 and 1 4. Certainly, this matrix is the symmetric matrix because transpose of this matrix is again the same matrix, and here if I just write x1 x2, here also x1 x2, and we can conclude that this is again our q x1 x2. That is why the quadratic form can be written in the symmetric form. Thus, in general, quadratic form is related with the symmetric matrix in matrix algebra. That thing has been written here, that q x1 x2 has been written in the quadratic form x c xt cx, as I have just told you. Now, we will just see further properties of the quadratic form. It tells us that if the quadratic form is greater than 0, then the corresponding matrix, rather the symmetric matrix, is being said as the matrix is positive definite. For example, just look at the example qx equal to x1 square plus 2x2 square. If you just see the expression here, for every x1 and x2 in the space, always q value will be greater than 0. That is why the corresponding matrix whatever we will get. What is the matrix for x1 square plus 2x2 square? If I just write down that matrix again, we will see that if I just write down the qx 1 x2 is equal to x1 square plus 2x2 square, then this matrix would be x1 x2, the quadratic form 1 0 0 2 and x1 x2. Certainly this matrix is the symmetric matrix. Not only that, this matrix is positive definite. Why? Because for every x1 and x2, this q value is always greater than 0, and for x equal to 0, q value is equal to 0. That is why we say the corresponding matrix is the positive definite matrix. Similarly, for the next, if the quadratic form is greater than equal to 0 for x not equal to 0, then the corresponding matrix is the corresponding quadratic form is positive semi-definite. Look at this expression. For example, the example has been given qx equal to x1 plus x2 whole square. If we just see this expression, we see for every x1 and x2, this value is always greater than equal to 0. When it will be equal to 0? When x1 will be equal to x2. And this quadratic form again can be written in terms of the symmetric matrix. Just see, qx1 x2 is given as x1 plus x2 whole square. That means this is equal to x1 square 2x1 x2 plus x2 square. That is why this can be written in terms of x1 x2 1 1 1 1 and this would be is equal to x1 x2, and this is again a symmetric matrix because A transpose is equal to A, alright. And not only that, for x1 equal to x2, always we will get the corresponding quadratic form as equal to 0. That is why for x not equal to 0, for every x1 x2 qx will be greater than equal to 0, for x equal to 0 it will be 0. That is why the corresponding matrix would be positive semi-definite. And if we see the sufficient condition involves a positive definiteness. For negative definiteness, here also another concept will be involved, that would be positive semi-definiteness and the negative semi-definiteness. Similarly, in this line we can say the one matrix, the quadratic form would be negative definite if qx lesser than 0, for x not equal to 0, qx equal to 0, for x equal to 0. For example, qx would be is equal to minus x1 square plus 2x2 square. For every x1 and x2, this the bracketed term would be always positive. That is why always the quadratic form would give you the negative value. That is why the corresponding form would be the negative definite. Similarly, here in the next negative semi-definite, where we are considering the relation qx less than equal to 0. And here for x1 equal to x2 only, the qx would be is equal to 0, otherwise for every non-zero x1 and x2, for every non-zero capital X, that is a vector x, the qx value will give us the negative value. That is why this is negative definite. But in the next, the example qx equal to x1 x2 plus x2 square, for different x1 x2 we cannot conclude anything about the sign of q. That is why for some cases, for some combination of x1 and x2, q will be positive, and for some combinations of the x1 and x2, the q value would be the negative value rather the non-positive value. That is why in that case we will say the corresponding quadratic form is the indefinite form. If this is so, then how to check the positive definiteness or the negative definiteness of a matrix? In general, checking the positive definiteness, negative definiteness from the given expression, it is not so easy. The examples I showed you, since those are involving only the two number of variables, that is why we could say very easily whether the quadratic form is positive or negative, or nothing can be said about that. But if we have n number of variables, more than 2 number of variables, 3, 4, 5, 6, looking at the expression of the quadratic form, it is not so always so easy to say whether the corresponding matrix is positive definite or positive semi definite, etc. That is why there should have some process to check it. The process is that we will, there are two processes rather. One process is that we will just see the principal minors of the determinant of the corresponding determinant. From there we will conclude this is either this way, or we will just look at the eigenvalues of the corresponding matrix. From there also we can conclude about the positive definiteness or the negative definiteness or semi definiteness or indefiniteness about the matrix. Now, if it will be positive definite, if the principal minor of A are all greater than 0, principal minor determinant means that kth principal minor would be, we will just consider first kth row and first kth column together, then that will give us kth principal minor. In that way, if we are having the matrix A11, A12, A13, A14, A21, A22, 23, A24, A31, A32, A33, A34, A41, 42, 43, 44. Then the first principal minor of this matrix would be A1. The first principal minor will give me the corresponding determinant. The second principal minor would be is equal to the first two rows and first two columns. That is why A11, A12, A21, A22. The third principal minor would be the first three rows and first three columns. That is why it would be A11, A12, A13, 21, 22, 23, 31, 32, 33. And the fourth principal minor will coincide with the given matrix, since the given matrix is of order 4. That is why here if we are having a matrix of size n by n, we can say that this is the first principal minor, second principal minor, this is the nth principal minor. If we see that all the determinant values are positive, then the corresponding quadratic form is positive definite. And if we see that the principal minor determinants are having the sign, alternate sign starting from negative, then the corresponding matrix corresponding quadratic form would be negative definite, and that is why k will run from 1 to n. The first principal minor will give me the negative value, second principal minor will give me the positive value, third one negative, fourth positive. In that way we will get the alternative sign. And similarly positive semi definiteness, we will have the principal minors which are all non-negative value. That is why some principal minor may have the 0 value as well. Then only we can say the corresponding form is the positive semi definite, the matrix. And similarly negative semi definite would be if we are having the alternative sign of the determinant values starting from negative. And indefinite, if we won't get any pattern, then we will say the corresponding matrix is indefinite in nature. This is one of that example, the same example we have taken before. Just see the example, 10x1 square plus 2x1 x2 plus 4x2 square. This can be written in the quadratic form in this way, x1 x2 10 1 1 4 x1 x2. This is a symmetric matrix for us. If we look at the principal minors, the first principal minor would be greater than 0, second principal minor the determinant value is again greater than 0. In that way, if we are having a big expression with few more number of variables, from there very easily we can conclude whether the corresponding quadratic form is positive definite or not. And that was one of the check, and this is the alternative check. Alternative check whether the matrix is positive definite or negative definite. It has been said that a matrix is positive definite if all the eigenvalues of the matrix are positive, and it is negative definite if all the eigenvalues of them are negative. Because we need this idea for when we are expressing the case whether the Hessian matrix is positive definite, we are concluding the corresponding extreme point is our minimum point, relative minimum point. If the Hessian matrix is negative definite, we are concluding that the corresponding extreme point is our maximum point, relative maximum point. That is why checking the positive definiteness, negative definiteness, these are very important for unconstrained optimization problem. Let us take an example where the function involves two variables x and y, and this is the expression x cube plus 3 y cube plus 3 x square plus 3 y square plus 24, and we want to have the extreme points first. For checking the extreme points, as we know, the necessary condition offers us the possible extreme members of the extreme points. That is why we will take the first order derivative, partial derivatives with respect to individual decision variables, and we will equate to 0. Del f del x1 is coming 3x1 square plus 6x, that is equal to 3x into x plus 2, and this we are equating to 0. We will get 2 points from here, one point x equal to 0 and another point x equal to minus 2. Similarly, from the second del f by del x2, we are getting 2 points for y, one is y equal to 0 and another one is y equal to minus 2 by 3. That is why we can say these are all the possible, these are all the extreme points we are getting from the necessary conditions. With every combinations of the x and y, we got just from the previous equations, we are getting 4 extreme points. Through these necessary conditions, we are getting the extreme points for function of several variable. Now, we do not know whether 0 0 or is the relative maxima or minima. That is why we need to have the next level check, that is the sufficient condition check for it. And for checking the sufficient condition, as I have proved that, we will just look at the property of the Hessian matrix, because the Hessian matrix will tell us whether the corresponding extreme point is the relative minimum or maximum or the saddle point. Rather, we will look for the quadratic form we are getting through the Hessian matrix, whether the quadratic form is positive or negative. Accordingly, we will conclude further. And this is the Hessian matrix for us. For this would be a 2 by 2 matrix, because we are having only 2 variables here, and del 2 f by del x2 we are getting from the previous, we are getting del f by del x1 as 3x square plus cxx, that is why del 2 f by del x1 square, I am sorry, here it should not be x1 x2, it should be x and y. Alright. In the next, we are having del 2 f by del x2 is equal to 6 into x plus 1, and del 2 f by del x del y would be is equal to 0, because del 2 f del f by del y was not involving any x component there, that is 0. This is our Hessian matrix. We will just see the nature of this Hessian matrix at different extreme points. That is why we will go for the principal minors of this Hessian matrix. Looking at the sign of the Hessian matrix, principal minors of this Hessian matrix, we can conclude whether the extreme points which we have, which we got from the necessary conditions, these are all the minimum or maximum or the saddle point. In this table, everything has been given in a nutshell. Just see, let us see the first extreme point 0 0, and our Hessian matrix was 6x. First, the Hessian matrix was this, the first principal minor was 6x plus c. At 0 0 point, the value is 0 here. The principal minor for the second principal minor at 0 0 point, it would be 6 6. That is why the value of this determinant would be is equal to 36 plus 36. And we see the first principal minor is positive, second principal minor positive. That is why we can say the corresponding Hessian matrix is positive definite. And we conclude that this is relative minimum, 0 0 is our relative minimum, and the corresponding functional value is 24. Go for the next extreme point, that is 0 comma minus 2 by 3. Again we will go back to the Hessian matrix, 0 minus 2 by 3, the first Hessian matrix, first principal minor is 0, first principal minor is 6 for us, and the second principal minor will give us some value, and this is the value for us, that is minus 36. That is why we cannot conclude anything from here, because the first principal minor will give us positive, second principal minor give us negative. But as I said, for the positive definiteness, all principal minors starting from the first, it would all would be positive, and for the negative definite, starting from the first principal minor, it would be alternate sign, but it will start from the negative sign. Since it is starting from the positive sign, first one is positive, next one is negative, that is why we conclude that the corresponding Hessian matrix is indefinite, and the corresponding extreme point is the saddle point for us. That saddle point means neither maximum nor minimum for the corresponding function, and this is the functional value 76/9 at that point. Similarly, the other extreme, third extreme point is -2 0. First Hessian matrix -12, second is again -72, both are negative. Again we cannot conclude anything, and the corresponding Hessian matrix is indefinite. Again this point is a saddle point. And go for the last one, -2/3. If we just see the first principal minor, it gives me the value, the negative value -6, and the second principal minor gives the value, that is positive value, +36. And since it is in the alternate sign, starting from the negative sign only, that is why we can conclude that corresponding Hessian matrix is negative definite, and the corresponding extreme point is the relative maximum point for us. That is why this is the corresponding value. Now, till now whatever we have learned for function of several variables, the necessary conditions gives us the possible extreme points, and sufficient condition tells us whether the extreme points we achieve, these are the relative minimum or relative maximum or the saddle point, but nothing we have said about the global optimality. Now, that is why we need to say something about the global optimality for this function. For example, this is the function for us. Now, whatever conditions we got, we will get this point as a relative maximum, this point as a relative minimum, this point as a relative maximum, this point as a relative minimum. But if we just look at the graph, we see this will offer us within this range. If this is the function is defined from A to B, then within this range, this is our global maximum. That is why whatever necessary and sufficient condition we have learned, that could not tell us anything about our global optimality. We need to know something more about this when we can say the extreme point is global maxima or global minima. That is why we are coming to the next for this. And it has been said that a concave function has a global maximum and a convex function has global minimum. Now, what is concave function, what is convex function, that we need to learn again. And we will see that convex and concave function again will be related with the positive definiteness and the negative definiteness, and rather the semi definiteness as well. But here just I want to mention that a concave function, we are considering the function n which involves n number of variables, and not only that, the function is the problem is unconstrained optimization. We will say if the objective function that which we are trying to optimize, if the corresponding function is a concave function, and whatever maximum we are achieving, that is the local maximum we are achieving, that is the global maximum for us. And if we see the function is global minimum, if we see the function is convex, then whatever minimum point we have achieved through the necessary and sufficient condition, the local rather the relative, this is the global minimum as well. But one thing we should mention here, let us see the pattern of a concave function and a convex function. Now, this function is a convex function, and this is a concave function for us. Now, how we can define the convex function and concave function? This is the convex function for us. If I consider a point here, say x1 point, this is corresponding fx1, this is our x, this is our fx. We are considering in of single variable only. This is our f function for us. We will say this f function is convex, fx is convex. If we take 2 points here, x1 and x2, and if we see that if we just take any point in between x1 and x2, say this is the point for us. This point can be written as lambda x1 plus 1 minus lambda x 2, where lambda is lying between 0 to 1. Then we can say, if we see the functional value at this point, any point in between x 1 and x 2 is lesser than equal to lambda into f x 1 plus 1 minus lambda into f x 2, then corresponding function is the convex function. And the reverse case, if we consider a point x 1 here and if we consider another point x 2 here, and in between if I consider any point here, then if we see at this point, that is lambda x 1 plus 1 minus lambda x 2, for lambda in between 0 to 1, if we put lambda equal to 0, we will get the point x 2. If we put lambda is equal to 1, we will get the point x 1, and if we want to get any point in between x 1 x 2, we will just vary the value for lambda from 0 to 1, and if we see this is greater than equal to f x 1 plus lambda into f x 1 plus 1 minus lambda into f x 2, then the corresponding function is the concave function. That is why if we see the objective function is concave function, then the corresponding min maxima we were getting the global, we will get the global maximum, and if we see the function is convex, then we will get the global minimum. But here one thing we should point it out, this global maxima or minima may not be unique one. For uniqueness, we should have the next condition is that we should have a strict convex function for global minimum, and we should have a strict concave function for global maximum. Strict means what? Whatever inequality we have achieved here, that equality sign should not be there. That is why we will get only one point here. There should not be any flat area where we will have several points where the equality holds. That is why we want to say that we should have only one point here, and strict convex means this inequality would be less than, strict concave means this would be greater than only. And for strict concave, and we will have the unique global maximum, and for strict convex we will have the unique global minimum. That is why looking at the functional pattern, whether the function is concave or convex, we can conclude about, we can say something about the global optimality of the unconstrained optimization problem. But again, the checking of the convexity reduces to the checking of positive definiteness and the negative definiteness of the matrix, because we know this property as well. If f is a function of n number of variables, then f is convex if we form the Hessian matrix, if this is positive semi definite, then the corresponding f function would be convex function. Similarly, if the Hessian matrix is negative semi definite, then the corresponding function will be the concave function. And for checking the positive definiteness, we know the principal minors will be all positive, the determinant values will be all positive, that semi definiteness, that is why greater than equal to sign is there. And for negative semi definite, we should have the alternate sign of the principal minors starting from negative value. But we know the other thing as well. If f is strictly convex everywhere within the given domain where the function is defined, then we will see the corresponding Hessian matrix will be positive definite. And similarly, for the, if we see the Hessian matrix is negative definite, then the corresponding f must be strictly concave everywhere. That is why looking at the Hessian matrix as well, we can check whether the function is strictly concave or strictly convex. That is why the Hessian matrix not only gives us the possible, the extreme points can check whether these are local maxima or local minima, but also it gives us the next level, that is whether the local minima or local maxima is our is again the global maxima or not. Here just one of the properties given here, let x star is a local or relative minimum, then x star is a unique global minima if there is a function from S to R, that is a real line, that is a, it is a, if function of several variable, then it should be S from to Rn. If f is strictly convex, then the relative minimum would be the global, unique global minimum. Let us prove it. Let us consider x star is the local minima for us. Then we know if x star is the local minima, then in the neighborhood, for example, this is the function for us. Now here this is the local minima for us. This is a local minima for us. How we will check this is a local minima? We will just look at if this is x star for us, we will just see the neighborhood of x star. If we see in the neighborhood this relation holds that f x greater than equal to f x star, then we will say the corresponding minima is the local minima for us, where x belongs to the delta neighborhood of x star. Now, x star we have to prove that x star is also the global minima. Now, let us assume that x star is not the global minima. We are having another global minima x hat within the domain of the function, that is S for us. Then if x hat is another global minima for us, then we can say that f x hat must be lesser than f x star. Now, with this condition, let us see further what is happening, and we have assumed that f is strictly convex. If f is strictly convex through the condition f of lambda x hat plus 1 minus lambda x star, this must be lesser than, it is not lesser than equal to, because this is strictly convex, lambda of f x hat plus 1 minus lambda f x star, where this point is a point in between x hat and x star. We have considered any point. If this holds, with this condition f x hat is lesser than f x star, we can further simplify it, and we are achieving to the condition that f lambda x hat and 1 minus lambda x star is less than f x star. This is the condition we are getting in. But if we consider lambda as very small amount, so that the lambda x hat plus 1 minus lambda x star would be in the delta neighborhood of x star. If we consider lambda very small, that would be very near to x star, that will be certainly in the neighborhood, delta neighborhood of x star. Then what we see in the delta neighborhood of x star, we are getting one point where functional value is lesser than the functional value at the extreme point. That is why whatever conclusion we made that x star is the local optima, then it is failing. That is why whatever assumption we made before, we have considered that x star is not global minima, but f is strictly convex, that assumption is totally wrong. That is why we can conclude that when f is strictly convex, whatever local minima we are getting, both that is the global minimum as well. This that is why we are taking the conclusion that x star is the global minima. Now, with the function is strictly convex, if the function is not strictly convex, if we are having the function, if we see the function is not strictly convex, function is convex only, that is why the lesser than equal to sign is involved there, then we will see that we will have several optima together we can have. But if we see the function is strictly convex, then in that case we won't get several global optima, we will get the unique global optima. That also we can prove it. We are considering one of the global optima x double star, which is different from x star, and if we take any point in between, that is considering lambda is equal to half, that is again within the domain of the function, and we see in that point the functional value is lesser than f x star. That is not acceptable to us because the function is strictly convex. That is why the less than sign is there, and x star we have assumed as the global minima. We should not have any other point where the functional value is lesser than that. That is why whatever we have assumed that we are having another global minima with x double star, that assumption was wrong. That is why x star cannot be, that is why we can conclude that we cannot have more than one x star when the function is strictly convex. That we concluding here that when f is the strictly convex function, then we can conclude that the corresponding local minima is the global minima. Similarly, when function f is the strictly concave function, the corresponding maxima, local maxima would be the global maxima. Now, for the next again we can prove that for strictly convex function, the corresponding Hessian matrix is positive definite. That is why whatever conclusion we made before, that if the function is we should have a relative minima if the function, if the Hessian matrix is positive definite. Here we are making further assumption that f is strictly convex, whatever local or relative minima we will get, that would be the global minima as well. That we can prove very easily. Just look at the function. This is the expression we are getting from the Taylor series. and since the function is the convex function, we can say this one as well. How we can say it? Let me just go through the graph once. Look at this graph. This is our convex function. That is why we are taking a tangent here, where the optima exist at x star. All right. We are considering another point, that is x star plus h, x star plus h here. This is our x, this is our f x. Then certainly function is the convex function for us. Not only that, we have considered only the function is strict convex function. Now, at x star plus h, this is the functional value. That is why the whole value up to this would be is equal to f of x star plus h. But up to this, if I just if I see this part, this value would be is equal to f x star, and what about this value? This value would be is equal to h del f, because if we consider the tangent here with the angle theta, this if this is h, then it would be is equal to h tan theta. Tan theta would be nothing but the slope of this tangent, that would be the first order partial derivative, that is a gradient function we are considering. That is why what we see that f x star is star plus h is greater than summation of f x star plus h of delta f at x star, and this is the reverse for the case of concave function. This is not the same for concave function. For the concave function, it will just reverse, f x star plus h must be lesser than f x star plus h, that is the gradient of f. That is why if I just combine these two conditions together, what we get? We get f x star plus h minus f x star is greater than this value. That is why what we conclude, that if the function is strictly convex, then the corresponding Hessian matrix is greater than 0. That is the conclusion for us. That is why we can say the Hessian matrix is positive. If it is positive definite, then the function is strictly convex. Now, whatever results we made out till now, we are summarizing all together right now. A convex function has a local minimum if at extreme point Hessian matrix is positive semi-definite. A strict convex function has a global minima if the Hessian matrix is positive definite everywhere, and a concave function has a local maxima if at extreme point the Hessian matrix is negative semi-definite. Okay? And a strict concave function has the global maximum if the Hessian matrix is negative definite everywhere. Whatever conclusion we just made up to this is very much related with the well known fact as a convex programming in optimization technique. We will just reconfirm all these results together in the convex programming further when we will consider some more complicated situation, that is the constraint optimization problem with several variables in the next. And that is we are concluding our lecture with this, that we can determine maxima minima for the unconstrained optimization problem where the objective function is continuous and differentiable. And we have said even not only that, we are not getting not only the local optimum, we are also getting the global optimum with further conditions we are having with the function objective function involved in the function in the problem, and these are the references can be referred for further learning of this topic.